So, welcome everyone to Guided Study Group, week 7 of Math 141. And so, today we're going to be starting on sequence and series. So, this is the first piece of material, but it's really important for midterm 2 because midterm 2 is not it's not going to be about integration. It's mostly going to be about series, power series, and like the convergence, divergence of series. So this is going to be the start of the main part of materials for exam 2. So sequence and series. First one is sequences. So yeah, can you please put your PSU ID in the chat room? That'll be great. Should we just type it out? Okay, so we have two parts this week. We're gonna be working on sequences and series. So sequence, definition of a sequence is a set of numbers written in a specific order. However, between each term, they don't necessarily have a link to one another. If you can just have like a random sequence, that's totally fine. It's still considered a sequence. That's one of the things also that will allow us to distinguish between sequence and series. Just give me a second now. Wrote down your issue ID. And so there's some sequences that we kind of like learn during the lectures. We have recursive sequence and Fibonacci sequence. So recursive sequence is that when you have the n term depending on the preceding term. So it's like an depends on a of n minus 1. So it, or like a to a of n minus 2. So a n minus 2 is kind of like we say the n minus 2 term of the sequence. And then we also have Fibonacci sequence, which is saying whatever term in the sequence is going to be the sum of the two preceding terms. So Fibonacci sequence is one of the recursive sequence. Then we have the definition of a convergent sequence. So a convergent sequence is that when you have limit of n approaching infinity of the n term of that sequence. So this is the n term of that sequence exists, and it has to be a number. And it's divergent if it's the limit does not exist, or it's plus or minus infinity. Next thing is that if we have like a combination of many sequences, you can find the limit of their n terms. So say if you have the sequence of an and bn, and so you can find if their combination is divergence or convergence using these limit law for sequences. Note the fact that you cannot use L'Hopital rule because L'Hopital rule does not apply for sequences. It has to apply for a specific function of variable. So what we learned in 6.8 cannot be applied here for L'Hopital rule. Like for this, if you have a quotient like this, do not use L'Hopital rule. Now, having said that, we have some other property of sequence. So a sequence can be monotonic and be bounded, Monotonic is when your sequences only have one train. It's either increasing or decreasing. But it cannot be both. So if the sequence is only increasing or only decreasing, it's monotonic. About a sequence. So when a sequence is said to be bounded above, if you have the nth term of that sequence always smaller than or equal to a number, and it's bounded below if the nth term of the sequence always bigger than or equal to a number. And this usually is the case with the trigonometric function, or some sort of like if you have a fractional function, and if you can prove the fact that it's always squeezed between those two numbers for the nth term, then that should work as well. Finally, we have some theorem. So for sequences, we can apply squeeze theorem. So it's saying if you have the n term of the free sequence, an, bn, and cn, and if bn is squeezed between, so the nth term is squeezed between an and cn for a certain amount of n, so maybe n bigger than 2, n bigger than or equal to 3, but n approaching infinity. And if you have limit that, so we need both conditions. So if you have a limit of n approaching infinity of the n term of the A sequence and n term of C sequence is approaching L as n approaching infinity, then you have Bn is also approaching. Limit of n approaching infinity of Bn also is L. And so this is kind of like just same thing for what we've learned so far about squeeze theorem. Then we have two other theorems, and the first one is really important. So when you have limit of n approaching infinity of absolute value of an is equal to 0, then the limit of n approaching infinity of an itself is also 0. And the second one is that if you can prove the fact that any sequences is bounded and monotonic, then you can immediately conclude that it's convergent. And so based on monotonic, this is what we learned, that make sure that it's increasing or decreasing. And bounded sequence, you have to make sure that it has to be bounded both above and both below. So bounded both above and below. See the bracket I use here. This is that you have to be both, and this one is either increasing or decreasing. Some other things is that in these sections, we're also introduced to a special sequence. So if you have a special sequence, it can be written in the form of a factor r to the n. So it's kind of like maybe 1 to the n, 2 to the n, or 3 to the n. Then this sequence is going to be convergent if that factor, the absolute value of that factor, is smaller than 1. And it's going to be convergent to 0. It's going to converge to 1 if that factor is 1. So there's no absolute value here. And finally, it will be divergent if you have that number smaller than or equal to -1 or bigger than 1. And so, the reason has been stated in the book or in your lecture notes. So I wouldn't mention the proof again here, but if you ever need help with the proof, let me know, email me, and then I'll get back to you. But maybe like schedule another Skype, and then we can talk in person. So let's start it with example 1. So the first 3 examples, 1, 2, and 3, are gonna base on determining if the sequence is convergent. So look at it here. So to find if a sequence is convergent or not, what we're interested in finding is that we're gonna find you have to find the limit of n approaching infinity of the nth term. If it's not a number, then we can conclude that this sequence is not convergent. So 1 minus 2 to the n to the 2n. And so from here, we look at something to the n. And so the thing inside, we can compare it using like the last thing that we learned over here. So let's look at that. So we have 1 minus 2 to the n is always is as n approaching infinity. So we have limit of n approaching infinity. Or actually, we can do this. And your n will start going from 1 to infinity. So we have 1 minus 2 to the n is always bigger than 0 and smaller than 1 for n smaller than n bigger than 2. Why? Because when n equal to 1, you have 1 minus 2 is going to be negative 1. But when n is equal to 2, you have n minus 1 is going to be 0. So it doesn't work until you have n bigger than 2, because when n bigger than 2, this is going to be a fraction smaller than 1 all the time. So when you have 1 minus that, the number will eventually be bigger than 1, because this fraction is smaller than 1. And smaller, the entire thing is smaller than 1 as well, because now it's 1 minus a positive number. And so here we're going to use the squeeze theorem. Actually, there's not many ways to do it, but I'm going to use the squeeze theorem because I think it shows the most solid proof for these questions. And so when you have limit of n approaching infinity, well, actually, when you make this one more, let's see how I actually solve this, because now I look about it, the squeeze theorem have a little problem with the second term we used to compare. So let's start it with looking at these terms and see what is it going to give us. So we have the first term of the sequence is negative 1 to the 2. Then we have 0 to the 4th. Then we have 1/3 to 6. And then we have things like n equal to 4, 1/2, n equal to 8. And so the terms in the next term is going to be n equal to 5, so it's 3/5 to the 10. And so having said that, we see from this is n equal to 1, 2, 3, 4, 5. Again, we're gonna make the kind of like reflection here that when you have n bigger than 2, 1 minus 2 over n absolute value is smaller than 1. Therefore, you can conclude that limit of n approaching infinity of 1 minus 2 to the n to the 2n is equal to 0. Because this is a smaller number, a number smaller than 1. And so when you take the absolute value of it and then you take it to the power of 2n, then based on what we learned before, like right here, we have that limit approaching 0. And so our conclusion here is that when you have an with n going from 3 to infinity, this one is convergent. And so from that, you can conclude that an in general is also convergent. Why? Because the first two terms are just two other numbers. So this is 1 and this is 0. But at n's approaching infinity, then it is going to be a very, very small number and it's almost 0. So it doesn't matter what is the first two term is, but it matters with the final term. What is the very last term as n approaching infinity? Where is it gonna approach? And if you can prove the fact that it's approaching 0, then, or like any kind of number, then we can conclude that it's convergent. I know this one is a little bit tricky if we try to use like the the squeeze theorem earlier, but now we can prove it this way. And if you try to use the squeeze theorem, you can also start it with when n is bigger than 2, then you have 0 is smaller than 1 minus 2 to the n, smaller than maybe 1/3, because, oh, this is not smaller than that. This is always bigger than or equal to. Yeah, I would say the squeeze theorem cannot really be used in these scenarios because if you look at the train here, the factor inside is going up from 1/3 to 1/2 to 3/5, so it's actually increasing. So if you use a squeeze theorem, unless you can identify, so you have like the first boundary and the second boundary, right? Unless you can identify a very suitable second boundary, then you can use a squeeze theorem. But if not, it's really hard to actually use the squeeze theorem here. Then we'll go to example 2. If you have any questions with example 1, just type it in the chat room and I'll try my best to answer your questions. So, example 2. Determine if a sequence is convergent or not, and if yes, again. So here, I'm going to write down the term that we have. So, you have n factorial over n to the n. So n factorial is written as n multiplied n minus 1, n minus 2, until we get to 1. And then in the denominator, we have n multiplied n to n. And so these two n can be cancelled out. And so what we end up having is now we have something like n minus 1 factorial over n to the n minus 1. Or we can just look at it in this way. Now, to determine if it's divergent or convergent, the way we're gonna do it is that look at this limit of n approaching infinity of an is going to be limit of n approaching infinity of this entire part. So n minus 1 over n multiply n minus 2 over n multiply until we have 2 over n and 1 over n. Now, looking at this one, you have limit of n approaching infinity of n minus 1 over n is 1. This is also 1. But here, as we go as we proceed with the terms, the limit is going to decrease until here you have 2 over n. The limit of n approaching infinity of this is going to be 0. This is also 0. And so in between, you're going to have some other limit, but it's going to be some other number. It's just going to be smaller and smaller than 1 and bigger than 0. So what end up happen is that we're going to have a tons of number multiply 0 and 0. So it's just going to be 0. And so we concluded that this is a convergent sequence. And so this one is all about making kind of like reflection, to look at the sequence and kind of like, okay, if you were able to split it out like n minus 1 to the n, multiply n minus 2 to the n, n minus 1 over n, multiply n minus 2 over n, and multiply, and we continuously go with that, then we kind of like, if you were able to find the individual limit, then you'll be able to find what is the limit of the entire big term of an. So that is example 2. So again, I would say in starting from this section, try to make a lot of like reflections or evaluation of the function, because sometimes I will say at this time it usually give you weird result, and it's kind of like a very different transition from what you've learned, like from integration to series and sequences. But try to practice a lot with that, and if you struggle, feel free to let me know where you struggle, and I'll try my best to help you guys out. Next is that we have example 3. Again, same questions. So here, it is a very weird sequence. So usually the terms that I'm gonna put on for these kind of sequence, just similar to example 1, is that I'm gonna write down terms and see where it's leading me to, and see if I'm able to make any reflections from it. So the first term, you have -1 to the 2 plus cosine of pi, and you have -1 to the 3rd plus cosine 2 pi, and you have -1 to the 4th plus cosine 3 pi, and so on. So this one, the first one is going to give me 0. This is n equal to 1, 2, 3. Maybe you can do the 4 to kind of like give us the feeling of where it's going. Second one is also 0. Third one, 0, and last one is also 0. Now, it's giving me the sense that every single term in the sequence is going to be 0. And if you continue to test, it exactly is going to be the case. So, based on this, we can immediately conclude that limit of n approaching infinity of an, or limit of n approaching infinity of this term, -1 to the n plus 1, plus cosine pi n, this is going to give you 0, because every single term in the sequence is going to be 0. So the nth term is going to be 0. And so again, this is also convergent. So one of the very good practice, as I just showed you, is that when you see a weird sequence, the first step, because you couldn't really imagine how it goes, first step is always try to write down some few terms, say like 4 or 5 first term, to see where the sequence is leading you to. Now that's all I have for section 11.1. Next one is 11.2 series. So series is a very different thing from sequences. Actually, series is formed from the sequence. So definition: series is the sum of infinite sequence term. So say if you have A1, A2, A3, going to AN as before. So your S1 is going to be A1, S2 is going to be A1 plus A2. Similarly, S3 is A1, A2, A3, the sum of all 3 of them. So it's a list of number with addition operation between them. Then so you have the definition of a partial sum. So Sn, and when n approaching infinity, limit of n approaching infinity of Sn is the sum from n equal to 1 to infinity of An. And this is demonstrated here. This sum is convergent if you have this limit approaching a number. But make sure that this is a limit of Sn, not An. So a convergent sequence can give you a divergence series. So make sure that you understand that part. So say if you have limit of n approaching infinity of An be a number, then you have limit of n approaching infinity of Sn. With Sn is the series that form from this An. It can be infinity or does not exist. So this thing can happen. This is possible. So if you have this limit exists, it say it's a convergent series, called convergent series. Now you have a distinction between a sequence and a series. So we see whatever. Okay. A sequence is a list of number. A series is a sum of a sequence and partial sum. So this is the list of number. It doesn't really need to have any relations between the terms. But here, every single term in the series have to have the addition like the link of addition between them. So the difference by a factor or a term in the sequence. Now properties. If you have two convergent series, their sum is also going to be sum, and difference is also going to be convergent. And if you multiply a convergent series by a factor, so the C multiply the nth term of a sequence by, and you take series of that, then it's also equal to that number C multiply the n partial sum. So I would say these are very clearly demonstrated in your lecture notes. So any struggle, first look at the lecture notes, second is the book, and third, if you still struggle, let me know, and I'll again schedule an individual meeting and figure things out with you. Then we have some series that we learn here, the special one when they have their own names, and we should be really familiar with them by the end of this this period when you prepare for midterm 2. Trigonometric series. So trigonometric series is that it can be written in the form of a series of a multiply the factor r to the n minus 1. So if you look at the terms, it's a plus ar plus a to r squared plus a to r cubed, or like each of them are different by, each of the term in the sequence are different by a factor r. So and you say so when you say you're gonna have a convergent series if the absolute value of r is smaller than 1. And again, if the absolute value of r is bigger than or equal to 1, then the series is divergent. And here we're gonna have just like a point of distinguish. We're gonna have a sequence of this be ar squared, ar cubed, going all the way to ar n minus 1. So this is what I have. For that, telescopic series. Telescopic series is kind of like one of the very representative form is that you can have like 1 minus a. So the n term can be like an, can be 1 minus 1 minus 1 over n minus 1 over m minus 1 or plus 1. So the next term, an plus 1, is going to be 1 over n plus 1 minus 1 over n plus 2. So it's kind of like some terms between the few terms right next to one another is going to cancel out, and it's going to make the entire sequence way easier to think about. So we also have that called method of differences. So the way that they're going to cancel out is by the difference, minus something and then plus something again. Finally, we have the harmonic series. So harmonic series, just by learning, and if you want to look at the proof, it's in the book. It's really helpful, but it's kind of like a little bit advanced. So if you want to like approach it, that's completely fine. I would highly recommend it if you have time. But if you already like struggle to understand the main thing, don't even you should focus on these first before you look for the proof of that. So then you have the harmonic series. This one is going to be always divergent. Then we have some theorem and some tests, which is really helpful. So the theorem saying if you have a convergent series, then the sequence that make up that series is also convergent and it converges to 0. Then we have a test of divergence. It's saying if you can find the limit of n approaching infinity of the n term in the sequence. No, it's a sequence, not the n term of a series. The limit of n approaching infinity of the n term of a sequence is different than 0 or does not exist, then you have a divergent series. One thing to be careful here is that when you find limit of n approaching infinity of an be 0, you cannot conclude anything about the series. This is because, as I said before, you can have a convergent sequence and still a divergent series. So it doesn't really tell you anything. But if you find it different than 0 or does not exist, it's for sure divergent. Now, and so now I would like excuse you guys for like a minute. And so who is the third participant? So Anthony Imicus, right? If you can please put your PSU ID in the chat room, that would be great. And also I will excuse you guys for 5 minutes for personal stuff. I really need to get to the restroom right now, so I'll be right back in 5 minutes. So okay, hopefully everyone has a chance to try these questions. And so for the first term of this, let's start writing out the sequences, and then we're gonna have the going along series. Or if you're going on, just start it. This is, so we have the sum from n equals 0, 1 to infinity. So you're gonna have of this inverse tangent minus inverse tangent. This one is going to, first is going to equal to inverse tangent of 1 minus inverse tangent of 2. So this is when n equal to 1 plus inverse tangent of 2 minus inverse tangent of 3. So this is when n equal to 2. And so if you continue to do that, eventually you have inverse tangent of n minus inverse tangent of n plus 1. And so this is when n equal to n, as n going to infinity. Now you can see the fact that I will write one more term here. Inverse tangent of 3 minus inverse tangent of 4. And so this is for if you're writing, it's not showing on my screen. Okay, can you see it now? I don't know what is going on with like the stuff. Can you see it, Samuel? Okay. This is weird. Why is it not showing? So here it started with, okay, so here we have that. So you can see the fact that from every single term is going to cancel out something. And here, see if between n equal 1 and n equal to 2, you're going to have inverse tangent of 2 cancel out. As the same thing, if you have between n equal to 2 and n equal to 3, you have inverse tangent of 3 cancel out. So what eventually is going to be left after this method of differences is that you're going to have inverse tangent of 1 minus inverse tangent of n plus 1, because this inverse tangent of n will have been cancelled by the negative inverse tangent of n before that. So this is when you, so to find this one, find limit of n approaching infinity. So to find if it's a divergent or convergent, or if it's find, eventually just find the n partial sum. So you have inverse tangent of 1 minus inverse tangent of n plus 1. So you can see here, inverse tangent of 1 is clearly pi over 4. And then again, when you're dealing with inverse trigonometry function, remember the domain and the range that I show you guys in the material of midterm 1. So kind of like make sure that you chose the right angle in the correct domain of that function or range of that function, because when you talk about inverse function, it matters if the function is 1-to-1 or not. So it's only 1-to-1 on specific domain or range. So make sure that you get that part. And when n approaching infinity, inverse tangent of infinity is going to be pi over 2. So this one's going to be negative pi over 4. And so just we'll talk about the graph of inverse tangent before. I think it's going to be something like this. So when n approaching infinity, so pi over 2 and then pi over negative pi over 2, the graph of inverse tangent is this way. So at n approaching infinity, the inverse tangent is going to approach pi over 2. So my answer for this one is that this is a convergent series, and limit of n approaching infinity of Sn, or like the n partial sum, it's going to be negative pi over 4. Note the fact that Sn here, so Sn is written in this form, and we do all the cancellations to get into this form. So this limit is essentially Sn. So any questions here? Okay, if not, I'm gonna go ahead to example 5. So example 5 is when you started to use the property of series. So looking at this one, if you keep it this way, and this is one of the tricks that I want to also show you, is that in the exam you're gonna be given, I would say either the quiz or the exam, you're gonna be given many times of a series in this form. And so the trick here is to be able to split them out and like evaluate them individually. So here, what we have is that, now let's don't care about the series first. Let's think about the n term. It's going to be 3 to the n minus 1 plus negative 4 to the n over 10 to the n. So splitting them out is that you're going to have this plus negative 4 over 10 to the n. Now let's do the simplification. So if you keep it in the form of 3 to the 2n minus 1 over 10 to the n, it is not as helpful as if you can put it in the form of some factor to the n like this. So what I'm going to do is that I'm going to put this thing as 9 to the n, multiply, or actually divided by 3, 10 to the n plus negative 2 over 5 to the n. So what I am having is two sequences that can actually form me two series. So the nth term is this one. So we have the sum of this is going to be the sum of 1/3 multiply 9 over 10 to the n plus negative 2 over 5 to the n. And we can separate them into two parts, which is going to be 1/3 sum of 9 over 10 to the n plus sum of negative 2 over 5 to the n. And so this, now we're looking back at the slides, we have that is the trigonometric series. And so first we have two factors of r. The first one we have the factor is 9 over 10, and the second we have the factor is negative 2 over 5. If you take the absolute value of both of them, you will notice the fact that the absolute value of both of them are smaller than 1. So the sum of that thing is going to equal a over 1 minus r. However, I would say when you try to remember this formula of sum, the very important thing to remember, and I think it's really helpful when you do the when you take the sum of a trigonometric series, is that you should know the meaning of a and r here instead of trying to put it in this form and then manipulate what is a and what is r, because most of the time you wouldn't be able to put it in that form at all. So I would say remember the meaning. The first term, the meaning is that a is going to be the first term in your sequences. So whatever the first term is here, it can be a multiply r. If this series starting from 2, you never know. So make sure that you remember what is the meaning. So the meaning of this is going to be the first term, and r is going to be the factor between terms in the sequence. So if you come back to this, now just remember the sum of geometric series is a over 1 minus r if it's convergent, and a is first term in the sequence, and this is the factor. So because here your sequence started at 1 and going to infinity, so we have 1/3. First term of this is when you have n equal to 1. So to find the first term, very easy. You just plug whatever n that you started with into that. So you have 9 over 10 minus over 1 minus 9 over 10. Because the factor here is also 9 over 10. Doing the same thing over there, you're going to have negative 2 over 5 over 1 minus of minus 2 over 5 is plus 2 over 5. So what we end up having is 1/3 multiply 9 minus 2 over 7. So what we end up having now is going to be 3 minus 2 over 7, which is going to give me 19 over 7. And let me check real quick if my answer match whatever we're having right here. Yeah, I don't have my answer, but it should work because I've checked through all the steps and it should matches the final answer. So the trick here, as I said, is being able to split them out into two sequences and evaluate them individually. And in most of the case, so looking at here, when you go from this step, I'll put it in red so that I see. When you go from this step to this step, you have to make sure that the two sequences that you're planning to use, the AN and, oh, I should just use BN. The two sequences that you're planning to use this formula, it has to be convergent before you use that formula, because if it's divergent, that formula doesn't even mean anything. So make sure that they are convergent first by comparing the factor r to 1. Sorry for like the slide just keep jumping around. Now let's go to the final example. Again, if you don't have any questions with the previous one, I'll just proceed because then I'll assume you guys understand it. Now this is a challenging one, and it kind of like struck me a little bit hard when I saw it, because I saw this one when I was doing a quiz in my class, and I would say, as I remember, none of them actually be able to solve it. I was able to solve this until half, and then I was stuck there. But then I was really surprised about what this actually means. So you're given that the partial sum of a series is 2017. What is limit of n approaching infinity of cosine 2 to an, with an is like the n term of a sequence. So you're given some property of the series, and you are asked to find the limit of the sequence. And in a moment, I was just like, what the heck does it mean? But there was one thing that I kind of remember at that time is that when you have a series and you were given the n term of the partial sum, so say this one mean the partial sum is 2017 as n approaching infinity. So it's 2017, and is this convergent? So the sum, so this is a convergent series. So there is a theorem that I kind of summarize is saying if you have a convergent series, the sequence is also convergent, and limit of n approaching infinity of an is 0. That is what we learned in that slide. And so having said this will allow you, you can find what the question is asking now. So you have limit of n approaching infinity cosine 2an minus 3 divided by 2an plus 3. Now you have limit of n approaching infinity of an is 0. So you're going to have cosine of 0 minus 3 divided by 0 plus 3. So what we have is 1 minus 3 over 3 is going to be negative 2 over 3. So the important part is being able to figure out this thing. So if you wouldn't be able to figure out this part, and so to figure out this, again, look back at the lecture notes and see some of the theorem that you were given, because I mean, most of the time we don't think that we're going to use a theorem ever, but in this case, the theorem is the key to solve the problem. And I would say it's going to apply a lot to the continued exercise that you're going to see in the in the next few sessions. So keep an eye on the theorem again. Now we're going to proceed to the last example, and this is also the longest one, because it's kind of like giving you 5 different series and asking you like determine if it's convergent or not. And so I would do this one quickly, because this one already kind of like go through a lot of the series that we already learned so far. At home, when you have time, you can try to have a look at these and like scrutinize it a little bit more thoroughly. But here I'm just gonna go through it quickly, because you guys already seen like enough series in both the lectures and the book and the exercise and all of that. If possible, I would recommend do this example 7 after you finish all the practice problems in the book, because that will be easier. You have like kind of like a holistic view of what kind of exercise and what kind of series we should expect from certain form. And so the first one, quickly, is going to be 3 over 4 to the n multiply 3. And this one, just looking at the r factor r equal to 3 over 4, smaller than 1. This is a convergent by the geometric series. And here, look at the questions. I'm only asking you if it's convergent or not. You don't need to find a sum, so that's good. Now, the second one is kind of hard, but this is also a sign that we can kind of like notice the telescopic series. Is that you're gonna, if you rewrite the denominator as n squared minus 1, and then you start to use partial fractions. I know you guys hate this. Partial fractions to find to separate this thing out into the difference of 2 fractions is going to be 1 over n minus 1 minus 1 over n plus 1. And so when you do this and you take n approaching infinity, this is going to give you 1 minus n should start at n equal to 2. So it's going to be 1 over 1 minus, if you write the terms out, you see what cancel out and what's not. Minus 3 plus 2 minus 4 plus 3 minus 5. If you continue to go, you have 1 minus m minus 2 minus n minus 1. When you have n equal to n minus 1, so you have n plus 1 over n minus 1 minus 1 over n plus 1. And so here, what end up cancel out is this, and then this, and continue term. But what's left is this one, and then if you have like a look at here, what you see is that it's going to have this term and this term left. And so I would say if you have more space, write everything out. It'll be way easier to see that. But then what we have is left is just 3/2 minus 1 over m minus 1 over m plus 1. And so when you take the limit of n approaching infinity of this entire thing, it is going to be, this one is 0 and 0, so it's going to be just 3/2. but I would say this one is an important one. And it's tricky because most of you didn't expect the fact that, okay, I'm going to have to use partial fractions and split them out to see a telescopic series and see how the term cancel out. And more importantly, more difficultly is that the term doesn't just cancel out from every single one. You have to look at 3 terms in a row and see some of them cancel out, some of them not, and you keep more than what you see in the example that I show you, I think example 4. So again, if you have a chance at home, relook this problem, because I think it's really important, the fact that you use so many technique, partial fractions, and also writing out a lot of that, and kind of like make a good observation of what cancel out and what's not. The next thing here is that this is going to use a test of divergence. How do you know we're going to use it? Well, I would say again, it's come from a lot of practice. And I would say practice is really important in these sections, especially for the materials of exam 2, like anything related to sequence series. Do a lot of practice, because this section, I would say, I think online in the math department website, you guys also have some extra practice problem called, I think there's some worksheet called series. So by just the name, it gives you like an impression that the difficulty level is going to increase. But I think those are the very helpful practice. And if you were able to do like half of the exercise in there, you more than prepare for the midterm 2. And to do that, I would say first, try all of the suggested problems in the book, and then my practice problem, and then those practice problem. Because I usually give my practice problem a level harder than what you guys should expect in the exam. And so it will be kind of like a better practice to prepare you guys for the exam. Again, coming back to this, how do you know you use test of divergence? One of the hints is that test of divergence saying, if you find the limit of n approaching infinity of the n term in the sequence, so just this thing, not the series part. So if you find that limit is equal to any number different than 0, or does not exist, then you have a divergent series. So here, when I look at this fraction, the first thing it gives me is, the first impression is that it gives me the highest degree in the numerator and the highest degree in the denominator. Give me the fact that if I take k approaching infinity, ak, then I'll have this limit approaching 1, and it's different from 0. So by test of divergence, you have a divergent series. And test of divergence can be really helpful sometimes. As you're going to see in the following sections, I will demonstrate more use of the test of divergence in the coming guided study groups. But this is one of the use where you can see a fractions, and you can notice the fact that the limit of that fractions at whatever k or n approaching infinity is not 0, or belong to like a different number, or it does not exist. Then you can use a test of divergence there. If you were asked just to find the convergence of the series, if you were asked to find the sum of a series, that might not be the best practice. But if you can prove the fact that it's divergent, there's no need to find a sum, because when you have a divergent series, it means the fact that there's no sum existing. Here in D, you have series of sine 100 to k. And so one of the things you should notice, and as I always say for trig function, is that you always have the fact that when you take absolute value of sine 100, it is definitely smaller than 1. So by the property of geometric series, this is smaller than or equal to 1. But you know the fact that it's not going to be equal to 1 ever, so it's smaller than 1. So then you have, this is the convergent series, because the factor is smaller than 1. Finally, when you look at E, again, in example 6, I demonstrate the fact that you have to split them out. So you're going to have 2 over e to the n and 4 over e to the n. However, when you split them out here and evaluate them individually, from 2 over e, you know 2 over e is a fraction smaller than 1. So you know that one is convergent. However, for the second one, 4 over e is bigger than 1. So when one of the component series is, let's say, make this, yeah. When one of the component series is divergent, then the entire thing is also divergent. Because it's composed of a convergent series and a divergent series, and so the entire thing is also divergent. So that's all I have for today. If you have any last minute questions with any of these exercises that I've been going through, if not, I'm just going to end the sessions here, and I have some practice problems here that you guys should really try out. And again, if you have any questions, any problem when you try these at home, feel free to email me. I'll get back to you guys as soon as possible. If not, thank you for coming here, guys, and I'll see you guys next week.